Have you ever wondered why electric vehicles are becoming so popular? Why has lithium-ion technology become dominant for electric vehicles? Does it really perform that well? Or are there challenges we need to know about? And could there be a better alternative? In this video, you'll find answers to all of these questions. Over the last decade, electric vehicle engineering has improved dramatically. Battery technology has become more efficient. Electric motors are now more powerful and compact. Charging infrastructure is expanding rapidly, and vehicle software is smarter than ever. At the same time, companies are investing billions of dollars into electric mobility. New startups are entering the market. Established global brands are now competing in this space. So the real question is, why has demand increased so rapidly today? The transportation sector contributes approximately 25 to 30% of global energy-related carbon dioxide emissions. Battery electric vehicles produce zero tailpipe carbon dioxide emissions during operation. Even when accounting for electricity generation, life cycle emissions are typically lower than those of internal combustion vehicles, especially as power grids increasingly incorporate renewable energy. Importantly, as electricity generation becomes cleaner over time, the carbon footprint of electric vehicles continues to decrease, unlike combustion vehicles, which remain emission-intensive throughout their lifespan. Internal combustion engines emit nitrogen oxides, carbon monoxide, particulate matter, and volatile organic compounds. These pollutants directly affect urban populations. Electric vehicles eliminate tailpipe emissions, significantly reducing exposure to harmful pollutants in cities. This has measurable public health implications, particularly for respiratory and cardiovascular diseases. Beyond removing tailpipe emissions, widespread electric vehicle adoption reduces smog formation and urban particulate concentration. Cities with higher electric vehicle penetration are already seeing improvements in air quality indices. This translates to lower healthcare costs and improved quality of life. Internal combustion engines operate at approximately 20 to 30% thermodynamic efficiency. In contrast, electric drivetrains operate at efficiencies of 85 to 90%. This means a significantly larger portion of input energy is converted into useful mechanical work. This efficiency advantage fundamentally changes energy economics in transportation. Electricity is generally cheaper per kilometer compared to gasoline or diesel. Additionally, electric vehicles contain fewer moving mechanical components. This reduces servicing requirements and long-term maintenance costs. Over the vehicle lifetime, total cost of ownership can be lower despite a higher initial purchase price. Electric vehicles can be powered by solar, wind, hydro, or nuclear energy. Furthermore, emerging vehicle-to-grid technologies allow electric vehicles to function as distributed energy storage units. This supports grid stability and enhances renewable energy utilization. Electric vehicles do not require oil changes, exhaust systems, or complex transmission systems. Regenerative braking reduces mechanical brake wear. The simplified powertrain architecture lowers failure probability and maintenance frequency. Transportation currently relies heavily on petroleum imports in many countries. Electrification diversifies energy sources. Electricity can be generated domestically from multiple resources. This reduces dependence on geopolitically sensitive oil markets and strengthens national energy resilience. In summary, electric vehicles offer environmental, economic, technological, and strategic advantages. Their benefits extend beyond transportation, influencing public health, climate policy, energy systems, and national security. For these reasons, electric vehicle adoption is not simply a trend, it is a structural transformation of the global energy ecosystem. Lithium-ion batteries became dominant in electric vehicles, but the real question is, why? Lithium-ion batteries offered a unique combination of advantages that perfectly match the needs of electric vehicles. Lithium-ion batteries typically achieve 250 to 300 watt-hours per kilogram at the cell level, with even higher values under optimized configurations. This high gravimetric energy density allows electric vehicles to achieve extended driving ranges without excessive vehicle mass. Given that vehicle mass directly impacts efficiency, acceleration, and structural design, this characteristic is fundamental to electric vehicle feasibility. Lithium-ion cells operate at approximately 3.6 to 3.7 volts per cell, significantly higher than alternative rechargeable chemistries such as nickel metal hydride. Higher cell voltage reduces the number of cells required in series to reach pack-level voltages, improving energy density and system efficiency while reducing interconnection complexity. Modern lithium-ion batteries can sustain 1,000 to 3,000 charge-discharge cycles, depending on chemistry and operating conditions. For electric vehicles, this translates into 8 to 15 years of operational lifespan. Advanced battery management systems further extend durability by controlling depth of discharge, temperature, and charge rate. Lithium-ion batteries typically demonstrate efficiencies exceeding 90%. This means that the majority of electrical energy stored during charging is recovered during discharge. High round-trip efficiency enhances overall vehicle energy performance and reduces operational energy losses. Lithium-ion chemistry allows rapid ion transport and low internal resistance, enabling high power output. This provides instant torque, strong acceleration, effective regenerative braking. High power density is particularly important in automotive applications where dynamic performance is required. Lithium-ion batteries exhibit relatively low self-discharge compared to other chemistries. This ensures that stored energy is retained efficiently during idle periods, enhancing reliability and storage stability. Over the past decade, significant global investment has established large-scale gigafactories. Mass production has driven substantial cost reductions, from approximately $1,000 per kilowatt-hour in 2010 to nearly $130 per kilowatt-hour today. This scalability is a key reason lithium-ion achieved commercial dominance. Lithium-ion technology benefits from decades of research. Ongoing advancements include silicon-dominant anodes, high-nickel cathodes, solid-state electrolytes, advanced thermal management. This sustained innovation ensures performance improvements and long-term viability. While lithium-ion batteries have enabled the global transition toward electric mobility, it is equally important to critically examine their limitations. No technology is perfect, and in research, understanding limitations is just as important as understanding advantages. Despite their dominance in electric vehicles, lithium-ion batteries face several technical, economic, and environmental challenges that must be addressed for long-term sustainability. These limitations influence cost, safety, lifespan, scalability, and environmental impact. Therefore, a balanced evaluation of lithium-ion technology requires us to carefully analyze these constraints. Although battery prices have declined significantly over the past decade, lithium-ion battery packs still represent approximately 30 to 40% of the total cost of an electric vehicle. This cost is driven by cathode materials such as nickel and cobalt, complex cell manufacturing processes, advanced battery management and thermal systems. While economies of scale continue to reduce cost, lithium-ion technology remains capital-intensive compared to conventional powertrain systems. Even at advanced performance levels, lithium-ion batteries achieve approximately 250 to 300 watt-hour per kilogram. In contrast, gasoline contains nearly 12,000 watt-hour per kilogram of chemical energy. Although electric drivetrains are significantly more efficient, the fundamental energy density gap results in increased battery mass and volume. This limitation becomes particularly critical in applications such as aviation, heavy-duty transport. Lithium-ion cells utilize flammable organic liquid electrolytes. Under abnormal conditions, such as overcharging, internal short circuits, or mechanical damage, exothermic reactions may initiate thermal runaway. Thermal runaway involves rapid temperature escalation, gas generation, potential fire or explosion. While modern safety systems mitigate these risks, the intrinsic chemical instability of liquid electrolytes remains a fundamental safety challenge. Lithium-ion batteries degrade due to complex electrochemical and mechanical processes, including solid electrolyte interface growth, lithium plating during high-rate charging, cathode phase transitions and microcracking, electrolyte oxidation at high voltage. These processes lead to capacity fade and increased internal resistance. Battery aging is strongly influenced by temperature, charge rate, and depth of discharge. High current densities during rapid charging increase electrochemical stress. This can promote lithium plating, accelerated solid electrolyte interface growth, elevated thermal stress. While fast charging improves consumer convenience, it creates a trade-off between charging speed and long-term durability. Lithium-ion batteries rely on materials such as lithium, nickel, cobalt, and graphite. Global supply chains for these materials are geographically concentrated and vulnerable to geopolitical instability. Cobalt mining in particular raises ethical and environmental concerns. As electric vehicle adoption accelerates, sustainable sourcing becomes increasingly critical. Although electric vehicles reduce operational emissions, battery production is energy intensive. Mining and refining activities may result in water depletion, habitat disruption, greenhouse gas emissions. Therefore, life cycle assessment must account for both operational and upstream environmental impacts. Lithium-ion batteries are highly sensitive to thermal conditions. At low temperatures, ionic conductivity decreases, internal resistance increases, power output and range decline. At elevated temperatures, degradation accelerates, safety risks increase. Effective thermal management systems are therefore essential in electric vehicle design. In summary, while lithium-ion batteries have enabled the rapid advancement of electric mobility, their limitations highlight the need for continued innovation. Addressing cost, safety, sustainability, and material constraints will determine the long-term viability of this technology. These challenges also motivate research into alternative chemistries and next-generation battery systems. Having critically examined the advantages and limitations of lithium-ion batteries, the natural question arises, is there a viable alternative? This brings us to sodium-ion batteries, a promising and increasingly researched energy storage technology. Are sodium-ion batteries really becoming a better alternative to lithium-ion? Can they solve the cost, safety, and material supply challenges we discussed? And are they ready to power the next generation of electric vehicles? If you're curious about these matters, this is something you don't want to miss. Click the link below and find out. Most importantly, if you want to stay updated on the energy revolution, hit the subscribe button and join the journey.